investigated the math function on my oscilloscope, I've come back to look at Paul Carlson's Wien generator, sine wave generator. Very pure, low harmonic distortion using a little light bulb. And as you can see, it is a very nice sine wave with his components almost exactly 1 kilohertz. And what's interesting, although you haven't got the comparison yet, is when you go to the math function, there is actually a frequency response potential, not just sort of straightforward channel 1 addition. You've got the fast Fourier transform in the form of various frequency, harmonic distortion potential by taking the readings of the various harmonics. And as you can see on this particular screen, there is no. So there's different views. So there's a flat top view, regular, Bartlett, rectangular, Blackman. That rectangular one was quite interesting, so that really pronounces the actual curve of the sine, make it highly visible. Blackman, and then Hanning seems to be the default, so I've left it at that. When you go to the cursor menu, you can move the cursors to actually get your measurements. So there's both or OS, and then turn the VO knob, and then you can get to the top of the peak. It doesn't seem to read exactly to the top, and it doesn't seem to be able to spread the waveform out. It just kind of moves the whole graph further along, and the higher you go up in the seconds per division, the slower it becomes in the sampling, I suppose. I've kind of lost it now. It's probably oscillating from banging the bench. Yeah, it's oscillating now. Yeah, it's gone. Yeah, it's oscillating again because I've hit the table, because it is very sensitive and it needs to be down at 12 volts, otherwise you get this kind of nonsense. But when it's stable and just at the right voltage without any movement, it's 11.5 volts there. Let's go back to this position, go back to the mass menu. Try not to touch the table. So there's the frequency spike at 1.05 kilohertz, and there are no other spikes, which I'll compare now with this sine generator here, which was a 20 quid one from eBay. That did have a first order harmonic, which if we have a look at that, so it should be running. This is only at 1 volt though, to be fair. To be fair to it, it needs to be on 20 to be, because this outputs, Carlson's outputs 20 volts. So to be fair, I suppose, make them equal. So there's 5 volts per division. So let's crank that up to 20 as well. So there's 5, 10. That's so that's 20 volts peak to peak, more or less the same now as Carlson's. But I think, I mean, it looks a very nice. Yeah, it looks a nice sign. It just, I don't know, it just doesn't seem to have. Maybe I'm imagining it. But anyway, the peak on this one. Yeah, typical now. It won't have the. It won't show it, will it? Probably. I jumped too far there. Oh, it's actually, it is very clean as well at that volume. So to be fair to it, there's no difference between that and that Carlson's, which is very pure, and the professional one. Just going to the cursor again and get into the peak of that. So again, so that one's very pure as well. There's no second order harmonics. So either one would be good to, and that of course is bang on 1 kilohertz as you'd expect from a proper programmable unit. So now it's a question of being able to put these signals through an amp and then do the calculations on however many second and third order harmonics there are, being able to read off the reference values and plug them into Alan AEW's equation on his YouTube video, and just see if I'm understanding this correctly to be able to get total harmonic distortion figures for a particular amplifier, putting this pure sine wave, these very pure sine waves, in as the signal source, and seeing what comes out the other end and how distorted it is and whether it's measurable, especially on things like these, the Technics amp. So that'll be the next stage when I've looked at it and can take some reading.